express a number in IEEE 754, which is also known as 32-bit single precision floating point format. So, which says that there are 32 bits to represent a floating point number in computer memory, of which the first bit towards the MSB is the Sine bit, and then the next 8 bits represent the exponent. It is biased exponent is represented in the 8 bit, and the Mantissa is the fraction part is represented by this 23 bits. Now let's take an example and see what is exponent, Mantissa and Sine. We have a decimal number and 241506800. So this is a very large number. So and we can also represent it using this way: 241506800 decimal point and then zeros. As you know that if we place a decimal point here and if we add the zeros to its right, these zero does not hold any value and does not add any value to this particular number. And we can represent this number, we can shift this decimal point towards the left of this number by incrementing the power of 10. So how many places are we going to shift this decimal point? 1, 2, 3, 4, 5, 6, 7, 8 and 9. So we are going to multiply the number by 10 raised to the power 9, and we shift the decimal point from its rightmost position to its leftmost position, and we represent the number in the following format. Okay, so first, and the sign, and since this is a positive number, the sign is positive. We generally do not write the positive sign in when representing positive numbers, so it is positive, so it's sign. Then this fraction that we have got is called as Mantissa, and the how many places the decimal point is shifted to its left is the exponent. So 10 raised to the power 9 becomes its exponent, and this is the Mantissa. In IEEE 754, we have a biased exponent. The biased exponent is of 8-bit value. So 2 raised to the power 8 comes out to be 256. So, but the actual range defined for this number is minus 126 to plus 128. Now let's take an example and see how we get the value of the biased exponent. Now we have this number represented in binary. If now there is a decimal point here and z which has a 0 value. If we move the decimal point from here to just uh, uh, just right of this MSB, we will get the decimal point here. So we move the decimal point 15 places to the left. In representing in IEEE 754, there is always a 1 outside the to the right of the decimal point. We do not include this 1, but this 1 is always uh, here. So the number becomes 1 decimal point and this number, which is same, and multiplied by 2 raised to the power 15. So the power of this 2 raised to the power 15 is added to a standard number, which is 127, and this number then gives us the bias point exponent. So 142 is the biased exponent, is 142. We have taken this number, so let's say this number has, so we moved the decimal point from this position to this position. So here is our decimal point. Now this exponent is added to this 127. This exponent is added to 127 and we got our 142. This is the biased exponent. Okay, and this part is the fractional part, or Mantissa, becomes its Mantissa. And let's say the sign is positive, so positive, we write a 0, and then this biased exponent 142 is converted to binary. Its binary is 100 1110. So the representation will be IEEE representation will be 0 for the sign bit, then 1000 1110 for the exponent, biased exponent, and then after that we will write the number from here to here. So let's write 0 110 1110 110101, and and zeros after that. Okay, uh, up to 23 bits. Okay, to 23 bits, this trail will go on, and this will become its Mantissa. Okay, so the number will become 0 for the sign bit, and this is 142 for the exponent, and and this Mantissa part is written over here, and if this number is not is small, if the digits are less than 23, then we add zeros to make it up to 23 bits.